In the previous video, you may have noticed something strange. While I was doing this, I used 100,000 records from perfect.mm, while I only had 1,000 records each from near-perfect.mm and streak.mm. Why? I needed more samples from perfect.mm to obtain a more robust or filled table of frequencies of critical counts. Like this. If there had only been a few thousands of perfect.mm records, some of the frequencies for certain critical counts would have yielded zeros. Here is the table for a better look. The critical counts in this table will be considered as categorical variables, not as just numbers. Then we may compare the frequencies of each category, critical count 0 to n, to other frequencies from comparing near-perfect.mm, streak.mm. The null hypothesis and the alternative hypothesis would be as below. But first, why do this? Imagine an immovable wall. It's made of a very perfect material called perfectium. This is a ball. It is also pure perfectium. We get another ball. This one is made out of a material called near-perfectium. Then this one, made of pure streakium. We are going to throw these balls at the wall and see how each one bounces and compare their behaviors. Being of different materials, they'll most likely behave differently, right? As you could probably guess, the immovable wall is the set of parameters from 1,000,000 perfect.mm records. The perfectium ball is the group of records each 300 games long from perfect.mm. The near-perfectium ball is the same but from near-perfect.mm. The streakium ball is the group of records each 300 games long from streak.mm. Throwing the balls at the wall was analogous to performing f-tests to compare variances. The behaviors of the balls, how much they bounce, where they land, the sound they make, etc., are the critical counts, their frequencies, and their relative ratios. These behaviors would need to be compared for further analysis of different materials and help us confirm that they are indeed different or not. And we will try comparing by using the chi-square goodness of fit test, since critical counts are now categorical variables. The purpose of this test would be to determine if the relative ratios of critical counts are identical or similar or different amongst the three balls when tested against the parameters. For our tests, we need something to always compare to, or what we can call for now as true ratios of critical counts. For this, we come back to this table and choose the range of critical counts that are to be included from 0 to n. Given that there are only 1,000 records for near-perfect.mm and streak.mm, and the critical count table is not as robust as the absolute values for the frequencies decrease as critical count increases, n was set to 22. So we will only use the parts in red to derive the true ratios for our next couple of tests. Here's the table for the true ratios. The null hypothesis and the alternative hypothesis would be as below. As a reminder, the purpose of the following tests will be to determine if the distribution of critical counts from a group of records from a specific matchmaking scheme follows the distribution of perfect.mm group versus parameters critical counts, or what we now consider as true critical count distribution. The degree of freedom will be 22, as there are 23 categories, and the threshold will be 40.289. If our value is bigger than 40.289, we will reject the null hypothesis. This table shows the results. The first row is obvious, as the test is being performed on the very sample that the true ratios are from. The second row shows that near perfectium behaved similarly enough, and with the test statistic being below the threshold, we should not reject the null hypothesis. The third row is tricky and requires some explanation. As seen previously in the last video, the histogram on the right shows that there are no records with 0 to 22 critical counts, the minimum being 130, not 0. This makes the chi-square goodness of fit test infeasible, because too many expected values become 0. So far, all the comparisons in this video have been between generated records. What about real records of games played by actual human players? How would those fare? How would a ball made of live datium behave when thrown at an immovable wall of perfectium? That was just a somewhat arbitrary depiction of the analogy. Here's what happened. We can have a new table of true ratios as there are more records of real players. Choose the range of critical counts that are to be included from 0 to 50. So we will only use the part in red to derive the true ratios for our next couple of tests. Here's the table for the true ratios. The null hypothesis and the alternative hypothesis would be as below. The degree of freedom will be 50, as there are 51 categories, and the threshold will be 76.154. If our value is bigger than 76.154, we will reject the null hypothesis. This table shows the results. Despite the minute margin that the bronze group exhibited, the table shows that no sample managed to keep the null hypothesis. This is intriguing as none of the histograms of live data resembled that of streak-mm versus parameters, where the distribution of critical counts were heavily left skewed. This may suggest that although invisible under simple inspection with our eyes, the distribution of critical counts of actual game records of real players is different to some extent in terms of the relative ratios of critical counts. We have observed that it is possible to distinguish which matchmaking algorithm may have been responsible for a group of records. By using their collective statistics, subtle differences may be found that suggest the use of one algorithm over another. It could be harder if the group of records is the result of more than one matchmaking scheme. Happy grinding, more videos coming soon.